Remember we said that when we first start up a motor, or we first send current through an inductor, that the current initially starts at 0 and has to slowly ramp up? Well, again, this is due to the fact that anytime we have a magnetic field, it takes energy to create this magnetic field. Okay, so again, we have our little inductor. Maybe this is the magnet in a motor, whatever. When we first start this up, okay, the current is going to take time to build up more and more and more as we generate our magnetic field. Okay, so it doesn't happen instantaneously. This magnetic field has energy, and we have to transfer the energy from the electricity, from the EMF source to the coil of wire. Well, how much energy does a magnetic field really have? Can we come up with an expression for this? Well, again, earlier we said that, all right, the EMF of a inductor, okay, is equal to the self-inductance or the inductance of the inductor times the change in current as a function of time. Now, we're going to take this equation right here and we're going to plug it in to this equation for power. Now, power is equal to current times voltage. So the current times the EMF is going to give us the power for an inductor. And we see that that becomes the current times the induction times the change in current divided by time. All right, where does this get us? Where are we going with this? So the power that is being transferred to the inductor, okay, due to this electrical circuit, which is going to be du dt, the power, the energy per unit time that we're transferring to that inductor as the magnetic field builds up, is equal to the current going through the inductor times the inductance times the rate at which the current builds. Okay? Okay, so if we integrate both sides with respect to t of this equation, okay, we integrate this side and this side both with respect to dt, okay, we are going to get that the energy in the inductor, okay, is equal, we haven't integrated yet, I lied, is going to be equal to the current times the induction times the rate at which the amount at which the current has increased, okay? I is where the current is right now. Di represents the infinitesimal amount of current that I add to the magnetic field, and du represents the infinitesimal amount of energy that the magnetic field increases in energy. So if I take this equation right here, now I'm going to do the integration, okay? I integrate both sides of the equation, okay? I get an expression for energy. L is a constant, so that can come out in front. I di, okay? If I integrate I with respect to I get I squared over 2, and I get this U equals 1/2 L I squared, okay? So that's the amount of energy that I get in a magnetic field due to a current in an inductor. All right, so once again, we know that the self-inductance is really related to how much magnetic flux I can build in there for the amount of current that I have. If I multiply that by the current squared, then divide by 2, that's the total energy. So again, the battery has to do work, okay? Has to do work to convert the electrical energy into a magnetic field. Work is probably not the best term to use here because work implies we're converting one type of energy into mechanical energy. But we can think about this as we are converting the electrical energy into magnetic energy. And again, if we look at one of these typical circuits and we watch what the current is doing as a function of time, okay? So here I have current, here I have time. It is going to take time for energy to be transferred to that magnetic field and the current to build up more and more, okay? And finally, when the current has reached a steady state, the current is just going to flow at a constant rate. Now, for alternating currents, we'll see that it's constantly changing, so it never reaches that steady state of maximum current. But again, just plugging in an electromagnet, when we do this, it will take time for energy to be transferred from the EMF to the magnetic field, okay? And that's why, that's why you just can't get a magnetic field suddenly go from 0 to, 1 Tesla. That doesn't happen. It takes time for it to build up, and it's based on how much energy we can transfer there. So let's calculate the energy stored in a 1 millihenry inductor, okay? I'm going to send 2.5 amps through that just to see, what a calculation might look like. So we use our equation right here that we derived earlier, plug in 4.5 millihenry, 2.5 amps. Remember, that's squared, so 2.5 times 2.5 is about 6.25. We multiply everything together and we see, well, it's not an insignificant amount of energy. We get about 14 millijoules of energy stored in that magnetic field. Okay,